Hello everyone, and welcome to this special recording for Deep Learning 11785. This is a one-off recording. This is not being done in class. It's not being streamed. We are covering a leftover topic, namely attention models, which are a specific instance of sequence-to-sequence models. What we have done so far is we've already seen the basic problems of sequence-to-sequence modeling. The problem is you're given a sequence x1 through xn of some symbols, and we want to produce from the network a different sequence of symbols y1 through yn. For example, in speech recognition, x1 through xn could be a sequence of feature vectors that go into the network. And what comes out is a word sequence, or alternately maybe a phoneme sequence or a character sequence. In the case of machine translation, a word sequence in one language would go in, and what would come out would be a word sequence in a completely different language. In general, the number of symbols that goes in is not going to be the same as the number of symbols that comes out, and we may not even expect a synchrony between the sequence that goes in and the sequence that comes out. So we've seen some examples of this sort of thing in the last class. In the speech recognition problem, for instance, a speech signal goes in. This would actually be a sequence of feature vectors, and a sequence of words would come out. Now, in this case, the sounds that go in occur in the same order as the words that come out. So there is some sort of a synchrony between the input and the output. In the case of machine translation, you might have a sequence like I ate an apple go in, and what comes out is Ich habe einen Apfel gegessen. So now here, if you look at the correspondence between the word sequence that went in, I ate an apple, and the word sequence that came out, Ich habe einen Apfel gegessen, you see that the words are not in the same order. So the first word I over here does correspond to the first word ish, but then here the last word is apple in English. In German, the corresponding word Apfel is the second to last word. Ate here is the second word. That actually becomes the last word in German. So the order has changed. There's no synchrony between the input and the output. So these two can be done with neural networks. And this is the kind of problem that we're actually going to be looking at today. Now, in the aligned case, where there is a synchrony between the input and the output, we saw in the last class a specific instance where the number of symbols coming out is equal to or lesser than the number of symbols going in which case, because there's some kind of a correspondence in order between the input and the output, we might say that this portion of the input corresponds to the first symbol of the output, that this portion of the input corresponds to the next symbol of the output, and so on. You could chunk up the input sequences into segments that correspond to individual symbols in the output. Like in the case of speech recognition, you would have some portion of speech that corresponds to a specific phoneme. Now, in the translation problem, we do not have this kind of synchrony. We may not even have a notion of alignment. For example, here we see that there's really no clear way of saying that they might act as a single word over here might actually split over multiple words in the output sequence. So here, for example, there is this word habe, which doesn't really have an equivalent word in the input. In fact, there are multiple words, habe gegessen, which are separated by two words, which map onto 8 in this case. So there's no real notion of alignment even. Now, before we proceed with explaining how we can address this problem, I want to recapitulate a parallel problem that we've already addressed or we've already looked at a couple of classes ago, and that is the problem of predicting text. So this is a simple problem. You're given a sequence of symbols, which might be a sequence of words, W1 through Wn, and the task is to predict the next symbol. What follows next? What's Wn plus 1? So for example, here would be the problem. What we want to do is to learn a model that can take a sequence of words, symbols, and produce the next symbol. So here, for example, it would take in W0 and produce W1. or it would take in W0 and W1 and produce W2, or W0, W1 and W2 and produce W3, and so on. So it must take in a sequence of symbols and predict the next symbol, and we can do this continuously. So as the input comes in at each time, it's always producing the next word. So if you look at the sequence of words until any time, what is being predicted is what is expected to be the next word. So we can actually, this is the prediction model we'd like to address. So here's a simple example of what we are trying to do. We might be given 4 and 7 years, and the question we must answer is what is the next word. In this case, obviously, it's going to be ago. Or I might have ABH, ABRAHAM, LIN, COL. What is the next character? In which case, the best prediction for the next character is going to be the letter N. So this kind of prediction is what we really want to do, except we want to do it continuously. So the way we saw we would do it is to have a model of this kind. The input would present the symbols as one-hot vectors. So each of these words is actually going to be represented as a one-hot vector over the vocabulary. The vector has zeros at every position except the position corresponding to the word being input, which would have a value of 1. And these one-hot vectors are mapped down to a lower dimensional embedding through a matrix P. And these are fed into a recurrent network. At each time, the network produces a probability distribution over all the words in the output alphabet. So for example, at this point, the network would be producing a probability distribution over all words given the first 3 words. So at any time t, the network is producing a set of probabilities YTI, where YTI is the probability of the ith word in the vocabulary, given all words from 0 to t minus 1. Now, to train this network, we would actually give it a sequence of words, and the target output is going to be the same sequence of words but shifted by 1, because when you give it W0, the desired output is W1. When you give it W0 and W1, the desired output is W2, and so on. So the target is actually the input sequence itself shifted by 1. The output, of course, is going to be a sequence of probability distributions. And so we will try to minimize a divergence between the target, which is just the input shifted by 1, and the sequence of output probability distributions. And if you use the cross entropy loss, this simply becomes a sum over all time instants of the cross entropy between the target word and the probability distribution produced by the network at that time. And the target word, of course, is going to be represented as a one-hot vector in order to be able to compute the cross entropy. And that eventually works out, as we've seen before, as the negative as the sum over all time of the log of the probability assigned to the target word at that time by the network. So we could minimize this divergence to learn the parameters of the network. Now, the hidden neurons themselves over here, although I've just represented it using just a simple single box, this could be a network of LSTM units, any number of layers deep. So it could be just a simple recurrent network, or it could be LSTMs. Either way is fine. But these could have any number of layers. I'm just simplifying the entire representation by showing it as one sequence of boxes. This entire structure can now be trained using backpropagation from a lot of text. Later, when I want to generate a text from this model, I would give it a initial sequence of words, say W1 through W3. And given the initial sequence of words, so before I continue, I want to point out that here I've explicitly represented the value of the hidden state at time -1. Typically, this is set to 0. So in some of these figures, I will not actually have this explicit box over here unless it's required. So now, when I want to produce text, I'm going to give it an initial sequence of words. And after the first initial sequence of words, say W1 to W3, have been provided to the net by me, for the 4th word, it will actually produce a probability distribution over the entire vocabulary. So it's going to produce a sequence of terms of this where YTI is the probability assigned by the net to the ith word in the vocabulary at time t, given all words until t minus 1. So at t equals 4, Y41 is the probability assigned to the first word in the vocabulary at time 4, given words 1 through 3. So from this distribution, we would draw a word, say W4. And now that W4 has been produced, we feed W4 back over here. So we have W1, W3, W1, W2, W3, and W4 occurs over here. This is fed back to the network, and now it will produce a probability distribution over words at time 5, from which we will choose a word. And we can continue this process until some termination criterion. Typically, for generating text, we represent the end of a stream of text by an end of sequence symbol, say represented by E or S, which is a special symbol included in the vocabulary which indicates the termination of a sequence and only occurs at the final position of sequences. So this generation would continue till one of these symbols became the end of sequence symbol. So that was about how we could model language and how we could produce a model that predicted the next word given all the words until the current time instant. We are going to actually use this model repeatedly in the rest of this lecture. So our problem now is that we are given a sequence of symbols or words, in this case, example, and we must learn a model which produces a different sequence of symbols. So in the machine translation problem, for instance, it gets a sequence of words. It must produce a different sequence of words. So this is very similar to producing text. Here again, the output is just a sequence of words, with one key difference in that it's not completely auto-generated. That generation is actually keyed in on by the sequence presented at the input. So the actual model is a variant of this model that we've seen in Karpathy's figures. It's a delayed sequence to sequence. You have the input sequence arriving, the input sequence stops at some time, and then the output sequence begins to be generated. Now, this is not a complete figure. The actual figure is better drawn in this manner. You have an input sequence which is processed, and when the input sequence is completely processed, some hidden value gets transferred to a second component of the neural network, which the recurrent neural network, which produces outputs where the output is now fed back to the input during the recurrence to produce the sequence of words at the output. Let's see this a little more explicitly. So first, the first component of this network is this first block, which is what we will call the encoder. The input sequence is fed to this recurrent structure, the encoder, and the input sequence, of course, is terminated by an explicit end of sequence symbol, as I mentioned. So as I feed the input sequence to this encoder, to this recurrent network, the first recurrent network, these hidden values are continuously updated until the final symbol, at which point this hidden activation, shown in red, carries or stores all the information about the entire input sentence. The information is continuously updated until this box here stores information about everything that went in principle. And once this is done, the second component of the recurrent network, which is this guy, which we will call the decoder, uses this hidden activation at the end of the sentence as an initial state to produce a sequence of outputs. And the output at each time becomes the input at the next time. This production continues until an end of sequence symbol is produced. So at the first time, using this hidden value over here, which has been produced after the entire input has been observed, that value is passed on to the decoder, which produces the first word. Now that first word is fed back into the decoder along with the current state, and the decoder then produces the second word, and then that second word is fed back in till it produces the third word, and so on. Once again, remember that at each time you're not really producing a word, you're producing a probability distribution over words, exactly as in the case of language generation, and we'll be drawing a word from this probability distribution. So this continues until the end of sequence symbol has been produced. So the actual hidden layer over here can be arbitrarily complex. You could just have one layer of LSTM units or even simple recurrent units, or you could have multiple layers. In the simplest model, the number of hidden layers in the output is going to be in the decoder portion of the network is going to be the same as the number of layers in the encoder portion. Now, there are different architectures possible. I'm going to continue using this simple representation with the understanding that these structures are also possible. And again, the portion of the network that actually processes the input to produce a single hidden representation that represents all of the information in the input, that is going to be called an encoder. The portion of the network that utilizes this representation of the input to generate an output sequence is going to be called a decoder. Now, let's take a little closer look at exactly how this network produces outputs. First, I want to point out that although I've just been using simple boxes to represent the input to this network is typically represented as a one-hot vector, which is then compressed to a lower dimensionality by some embedding matrix. And the embedding matrix that you would use for the source symbol sequence in this case is going to be different from the embedding matrix for the target symbol sequence, because the two might be completely different vocabularies. So this would be the embedding for English, this would be the embedding for German. Again, there are different variants possible over here. If the input and output are both from the same language, as we will see in one particular example, then we'd expect P1 to be the same as P2. In other cases, the two might not be the same. If the input actually consists of a sequence of real valued vectors, then you might not have an embedding at all. These are all different variants. Without getting into details, I'm actually not going to show this layer in my illustrations. I just use the simpler illustration where the input goes directly to the hidden layer. So now let's look at how this network actually produces outputs. Once the input has been processed and we have a hidden representation, that hidden representation is going to be fed to the output unit of the decoder, and the output unit actually produces a probability distribution. It produces a probability distribution for the first word in the output sequence given the entire input sequence. So this one over here is the probability of the first output word given all of these words. Then from this distribution we draw a word, and once we draw the word, we feed it back into the network, and the decoder now processes the combination of the word that has been generated here and the current hidden state to produce the next probability distribution. And now this probability distribution is the probability of the words that occur in the second position in the output sequence given the entire input and the first word in the output sequence. And from this you draw a word and you'd feed that back in, and the entire process continues. So observe that at each time the output of the network is going to be the output of the network is going to be the probability distribution over all words at that time given the entire input sequence and the entire output until the previous time. So at this point, the probability distribution that you get over here is going to be the probability distribution over words at time 2 given the entire input sequence and the output at time 0 and time 1. Or in this case, I have indexed from 1. And from this distribution, we'd be drawing a word, and we'd be continuing this process until an end of sequence symbol has been generated. Now, this is the whole process. At each time, the network produces a probability distribution over words given the entire input and the output until that time. We draw a word from this probability distribution, and this is provided as an input to the next time, and we continue this till we get the end of sequence symbol. So what are we really doing in the process? If you actually multiply the probabilities of the words chosen at each time, So if you just multiply these y terms for all of the words that were chosen at each time, that is going to give you the probability of the output sequence of words given the input sequence of words. So for example, if I multiplied y1 ish, y2 habe, y3 einen, y4 Apfel, y5 gegessen, y6 end of sequence symbol, that's simply the probability of ich habe einen Apfel gegessen given I eat an apple. Right. So observe that the probability of the output word sequence is simply the product of the probabilities of the words given by the network at each time. And what we would like to do is to produce the most probable word sequence. So we want to find the word sequence for which this product is maximum. Now, one way to do it is to simply pick the most probable word at each time and feed it to the next instant, and then pick the most probable word at the second time and feed it to the network at the next instant, and so on. But doing this tends to be suboptimal because this may cause the distribution to be more confused at the next time, and choosing a different, less likely word would cause the distribution at the next time to be more peaky, resulting in a more likely output overall. So to illustrate this, let me give you a hypothetical example. Say we were performing speech recognition. So the input is a sequence of feature vectors derived from speech, and we're trying to predict what was spoken. So let's say that for the first word chosen, for the first word, the most likely word was the word he. And so we chose the word he. Then for the next word, perhaps the word nose, as in nose, N-O-S-E, has slightly greater probability than the word nose, as in with K-N-O-W-S. In this case, I would just choose nose, although K-N-O-W-S also has a high probability, not just as much. Now, what follows he knows, where this word is the organ nose? Now, in this case, the he knows doesn't really have a very plausible next word. So the network would be confused over all possible words for the next symbol and assign somewhat uniform but low probabilities for all the words. Whereas if I had not chosen NOSC at this point and I had chosen KNOWS, this knows, now in this case, words like, sentences like he knows something are obviously very clear constructs, and so you would expect the probability distribution over words that the network outputs at the next time to have some clear peaks for some words that just nicely fit. So what would happen here is that although knows, as in this knows, has a very higher probability over here, if I multiply the probability of he, this knows, and the highest probability of this lot, that might actually end up being lower than the probability of he times the probability of knows and the highest probability of this lot. So although after 2 words, he knows had the higher probability, after 3 words, the sequence of words that we got with KNOWS was higher in this case. And this kind of effect may not even be immediate. In fact, this kind of effect could occur over any amount of after any amount of delay. So here, for example, so the problem here is that it's impossible to know a priori which of the words we choose over here leads to a higher probability output sequence overall. Which of them leads to a more promising future? Should we draw nose or knose? The effect may not even be obvious immediately. In this example, it's the way I presented it, the effect was immediately apparent. But more generally, the effect may not be obvious. The incremental differences may be cumulative, and the difference between the effect of the bad choice might not be evident until several words into the sentence. So the choice of the wrong word early may cumulatively lead to a poorer overall score over time. And this, in fact, it doesn't have to start at the second word. It could, in this example, it could have started at the first word. For instance, let's say that the 2 possible words for the first word were the and he, where he was slightly more probable than the. If we just chose he because he was more probable, then we are already stuck with not being able to predict nose. On the other hand, if you had chosen the, then the nose is a perfectly plausible beginning to a sentence. And so that might have led downstream to a much more probable sentence overall. So here we have the problem. It's impossible to know a priori which word leads to the more promising future. So here, for example, choosing the lower probability the instead of he may have made a choice of nose more reasonable at t equals 1. In general, making a poor choice at any time commits us potentially to a pure future, but we cannot know at that time that the choice was poor. So for example, at this time when we chose he instead of the, we had no way of knowing that 5 words downstream this is going to cause a confusion and it's going to cause low probabilities to the predicted sequence of words. So what is the solution? Let's not make a choice. What we will do is to actually fork our network. What I mean by this is that at this point, once I've done encoding my input, I'm going to make as many copies of my decoder as I have words in my vocabulary. And I'm going to pass this value to each one of these copies. Now, each of these is going to produce a probability distribution over words, and each of these is now going to, wait, let me correct myself. So once I've done with the decoder, at the first time instant, I'm going to produce a probability distribution over words. So and then I would make as many copies of my decoder as there are words in my vocabulary, and I would take each one of these words in the output and feed that as input to these copies. So this one might take I as the output, as the generated word. This would use he as the generated word. This would use we, this would use these. So there were many words possible over here. Each of them had its own probability. All of these words are going to be fed individually to different copies of the decoder. So at this point, each of these copies is going to produce a probability distribution over words. So at the next instant, I'm going to feed every one of those words as a possible input to the decoder which means that the decoder forks again. So each of these copies is going to have as many children as there are words in my vocabulary. Now you can see the problem with this. If my output vocabulary has size v, after t output steps, we would have forked out v raised to t possible branches, and this is going to blow up very quickly. So the solution is we will prune. At each time, we are going to retain only the top k scoring forks. So for example, at this time, I have a probability distribution over all words, but instead of using all of the words as possible futures, I will use only the top, say, 2 as possible futures and feed only those 2 words, and I'll fork only 2 copies of my network. Now at each of these guys in turn is going to have v possible outputs, right? But then of these v possible outputs, so since I have 2 of these guys over here, I'm going to have 2v possible branches to my network. Of these 2v possible branches, I'm going to retain only the top k, in this case k equals 2. So now the network is down to this, right? And now these the next time again, these can be forked off, and I'm going to have 2v possible branches, but then I'm only going to retain the 2 branches which are most probable. And how do I compute the most probable branches? It's going to be the branches for which the product of the probabilities until that branch is highest. So here, if you look at if I have the total number of branches over here starting from the root, I have 1, 2, v branches here, v branches here. I have 2v possible branches. For each of the 2v possible branches, the probabilities until here are of course common, but then these would get multiplied by the input probabilities, the probabilities of the input symbols for each of these guys. So you're going to have 2v different probabilities, right, of which I retain only the top 2. And I keep continuing this, at each time retaining only the top k scoring forks. And I would keep continuing to produce outputs in this manner until I got an overall I got a path that ended with the end of sequence symbol and which had the highest possible probability of all paths that were still alive. So here I have two paths that are alive. Now if the end of the path, the total cumulative probability of the path until here was higher than the cumulative probability of the path until here, then I would output this. But what if this guy was higher? Then I would continue, but now because this is already stopped, I cannot have any more symbols after the end of sequence symbol. This lower branch is the only one that would begin forking out. And so I would keep continuing this until I got to a situation where any one of these paths that ended in an end of sequence symbol had the highest overall probability, and that is what I would output. I could also output not just the one most probable word sequence, I could output sequence, I could also be outputting the n most probable output sequences. Different options are possible. Now in my example, I have pruned to use only the top two most probable outputs. In general, you can use any number k, where k is a configurable number. So we've seen how we can produce an output from this network. How about training the system? To train the system, we must learn to make predictions appropriately. So given I ate an apple, we must train it so that it's able to produce Ich habe einen Apfel gegessen. So now in this case, what I would is compute, this is what I would do. I would have the complete encoder-decoder sequence. The encoder would be given I ate an apple, end of symbol. The decoder is going to be given Ich habe einen Apfel gegessen as also as the input. So, and at each time, the decoder is going to be producing a probability distribution over all possible words, right? So now observe that I'm actually also feeding the target output to the network during training. Why am I doing that? So at this time, I want the output ideally to be ish. And at this time, I want ish to be the input, and I want the output to ideally be habe, right? And so on. So at any time, you not only need all the inputs, but all the outputs until that time to be fed to the network. So observe that in order to, even during the forward pass of training, I'm actually using both the target, the input and the target outputs as the input to the network. And this is going to produce a probability distribution at each time over all of the words. And then of course I have the desired output, right? At the first time instant, the desired output is ish. The second time instant, the desired output given the entire input in ish is habe. At the third time instant, given the entire input in the first two words, the desired output is einen, and so on. So now I can compute a divergence between the desired outputs and the probability distributions output by the actually output by the network. And I can backpropagate the derivatives of these divergences backwards to update all of the parameters of my network using the standard backpropagation rules and update rules for recurrent neural networks, now or LSTMs. More practically, when you're doing something like stochastic gradient descent, you tend to sample. So what you would do is that you would present each input, which is going to be an input-output pair, and the forward pass is going to produce the probability distributions for all of the outputs, and you'd randomly choose any one time instant and backpropagate the derivatives of the divergence at that time instant to update parameters. So, but then there are different combinations possible. They're different, and I've seen different suggestions as to which of them works better. Anyway, here's the overall training. Given several training instances, X and D, right, where X is the input sequence, D is the desired output sequence. During the forward pass, you're going to compute the output of the network given X and D. Now observe again that during the forward pass, you are not only inputting the input sequence X, but because of the manner in which we are using the decoder is actually being used as a predictor for the next output symbol given all previous output symbols. Even D is used during the forward pass. This differs from conventional training of neural networks where only the input is provided during the forward pass and the desired output is only used to compute the divergence. Here the desired output is also input to the network. And during the backward pass, you compute the divergence between the desired target output D and the actual output, which is a sequence of probability distributions, and you propagate the derivatives for updates. Now, there's a common trick that's employed in these kinds of models. Instead of providing the input in linear left to right order, instead of saying I, 8, and apple, end of sequence, you provide the input in reverse order. So it goes I, end of sequence, apple, and 8, I. The length is still the same. The reason for this is that typically you expect the first symbol and the input to be most relevant to the first symbol and the output. And so providing things in this reverse order seems to result in better predictions for the output. And of course, the back propagation proceeds just as usual. Now, this is done both during training. So during training, you provide the inputs in reverse order, and during the actual operation, during decoding, where too you provide the inputs in the reverse order. So the training algorithm in this case is the same as before, except now the input is going to be presented in reverse order. So let's look at some applications. Standard applications for these sequence-to-sequence models are machine translation. So you might want an input like my name is Tom, and you want outputs such as ich heiße Tom or mein Name ist Tom. Or automatic speech recognition. The input would be a sequence of feature vectors derived from the speech, and you want the output to be a sequence of words like my name is Tom. Or dialogue systems. So in conversational systems, you have two agents talking, an agent and a customer typically, or two people talking to one another. But A speaks and B responds. Now, can we actually replace this B using a neural network? This turns out to be exactly a sequence-to-sequence problem. We'll see an example of this. Or we could also use this for generating captions for images. So going from images to text. Now, here is a very nice example of what happens when you use this model for machine translations. This is from sequence-to-sequence learning with neural networks by Sutskever et al. Here, after having trained the network, they provided the network with various sentences as inputs and observed that this encoded output is going to be a fixed length vector regardless of the length of the input sequence. And they actually projected this vector down to 2 dimensions using principal component analysis just to be able to visualize sentences went, and in this 2-dimensional principal component plane observed that sentences seem to be clustering together. So Mary admires Tom is very close to Mary is in love with Tom. It's somewhat more distant from Mary respects Tom, but it's quite distant from John admires Mary, which is an inverted meaning. John admires Mary is close to John is in love with Mary, and John to John respects Tom. So observe that you have this nice clustering, semantic clustering of these sentences. You have more examples of the same kind on the right-hand side. So this hidden representation that's learned, that's shown by the red box in the figure, actually seems to capture some semantic structure in the input sentences. Here are some examples presented in the same paper on translation to French. I wish I could tell you it was good, but I don't understand French. I can't even try to read French. So, but if you're interested, you can either look up their paper or just look at the slides, and I'm informed that these are actually pretty good translations. Here is an example of human-machine conversation. So in this example, they collected, this is by Oren Vinyals and Kwok Lei, a neural conversation model. They collected lots of examples of people talking to agents over chat. So you have someone like a customer speaking to an agent response. Now you can think of this entire process as a translation model. The input is the customer's query. The output is the agent's response. Can we replace the agent by a sequence-to-sequence model? That's exactly what they tried over here. And you can see that it does a pretty good job. So the machine begins with, what is the error that you're running, please? And the human says, I'm seeing an error related to VPN. This is automatically generated by the machine. What is the error message that you're getting when connecting to VPN using Network Connect? So this is generated by the machine. The human response, connection refused, or something like that. And this is again generated by the machine in response to this input. May I know the version of Network Connect? You connect. So it's broken grammatically, but you can see that it's actually giving a very reasonable, plausible output. It seems to be performing well. The sequence-to-sequence model even seems to be able to capture the structure of conversations. In this case, both input and output are obviously the same language. Here is an even more interesting application. This is not really a sequence-to-sequence problem, more an image-to-sequence problem. Here, instead of using an input sequence of words in the encoder, we use an image which is passed through an image recognition network. So the encoder is actually an image recognition network, and the output of that is passed on to the decoder. So this is from Show and Tell, a neural image caption generated by Vinyals et al. Here's how the system actually works. When it's actually decoding, when it's actually trying to generate a caption for an image. The image is initially fed into a convolutional neural network, and the output of this is an image classification network, state-of-art image classification network. So the output of the image classification network, once you get to the classification layer, is going to be a probability distribution over all possible objects detected in the network. This output layer is fed to the first hidden state of the decoder, which then uses it to produce a probability distribution over words, from which you draw a word and you go through the usual decoding process from there on until you get to an end of sequence symbol, right? Now, you wouldn't actually be using a straight up decoding by picking the most likely word at each time. You'd be actually use the beam search, the pruned beam search mechanism I just explained a few minutes ago. And for training, you'll be given several image caption pairs. The image network, this one, is pre-trained on a large corpus, for example, ImageNet. And subsequently, given you just feed in the image, the classification output of the image recognition network, and the captions assigned to the image in the training data. The network, of course, will produce a probability distribution over words at each time. You can compute the divergence between the target output and this probability distribution. The target output is going to be the same as the caption given to the image in the training data, as you can see. And these divergences can be fed back to train all of the parameters of the network. The one component of the network that is not actually adapted is the convolutional portion of this image classification network, although the final classification layer itself might be updated. So we are using the CNN portion of the network trained from a very large corpus of, say, ImageNet data as a nice feature extraction mechanism within a transfer learning framework. This whole mechanism works really well. So here we've seen these examples earlier in class. Here's an image, and here is the caption assigned to it by the network. Man in black shirt is playing a guitar. Construction worker in orange safety vest is working on a road. Two young girls are playing with a Lego toy. Boy is doing backflip on a wakeboard. It also makes mistakes, like a young boy is holding a baseball bat, or I'm not really sure where it got this from. A horse is standing in the middle of a road. Now, mistakes of this kind can arise from different reasons. It might be that the image classification network just erroneously found a horse in this picture, or that the language generation chose the wrong sequence of words to stitch together the objects found by the image classification network. Regardless, these results are quite impressive. So you see, this thing works really well. And there were other extensions where people have used this for finding captions for videos, where you pass all of the frames of the video through a CNN, and then you pass you pool the outputs of the CNNs across all time, and feed these to the LSTMs that actually produce the captions. So there were other variants, and the latest state of the art in generating captions for images is actually pretty impressive. Anyway, so you get the idea. It's a very simple model, and it's able to convert one sequence to another quite effectively. However, it has a problem, and the problem is that the encoder compresses all of the information about the input sequence into this one box, which is the hidden representation of the encoder at the end of the sentence. So this hidden node at the end of the input sequence is expected to carry all of the information about the entire input, regardless of how long the input is. And clearly, this is going to be a problem. As the input gets longer and longer, you're imposing a greater and greater load on this final hidden representation. This one node ends up being overloaded with information, particularly if the input is long. Whereas the fact of the matter is, all of these hidden units carry some information about what the output must be. And if this hidden unit carries some information about some portion of the output, by the time this information is passed down to this final box here, that information may in fact get diluted. Whereas we know that if you consider the actual output, there is to some degree a direct correspondence between the desired output and the input sequence. So here, for example, this H over here directly relates to I. So it must have a more direct correspondence to the hidden representation here than, say, the one over here. Similarly, einen has a more direct correspondence to this guy, which is connected closely to an. Now 8 has direct correspondence to both Haber and Gigasen. So you can see that different words in the output actually depend more directly on different entries, the hidden entries at different times in the input. And simply trying to compress all of these guys into this final vector over here can be expected to lose information about what happened earlier in the sequence, and as a consequence result in poorer output sequences. So one way to do this, of course, is to say I'm going to just take all of these hidden representations and feed them to the output at each time, to the hidden layer at each time. Now it's nice to draw. It's not practical. Why? Because we have no idea how long the input is going to be. We have no idea how long the output is going to be. So we really this is not a fixed architecture. We have no idea how many weights we must have in this kind of network, because the input and output are arbitrarily long. Moreover, if I use the same weight structure over here as I do over here, then basically you are sort of ignoring the fact that the dependence between the output sequence and the input sequence is not necessarily synchronous. Those dependencies might cross over. So what we really want is something that captures this implicit dependency structure, and for that we will use an attention model. First, to explain the attention model, I'm going to sort of redraw my figure a little bit by drawing the input and output, the encoder and decoder at different levels, so that we can visualize things cleanly. The figure to the right is the decoder, the figure to the left is the encoder. Now observe that I'm using H-1 and S-1 for both the encoder and the decoder. This H-1 is typically set to 0, but you might also learn it. How this is set ends up being somewhat important to the process of decoding, so I will leave that in place. Now what the attention model does is that instead of having a direct connection from all of these hidden units to each of the hidden units over here, at each time we will compute a weighted combination of all of these hidden units. So for example, at time 1, you're going to compute some W01 times H0 plus W11 times H1 plus W21 times H2 plus W31 times H3 plus W41 times H4. So this is the weighted combination of all of these inputs that's computed, and that goes into the hidden layer over here. At the next time, we will compute a different weighted combination of these inputs, of these hidden representations. Observe that the encoder, once it has processed the input, has already computed all of these hidden representations. Those are fixed. All we are doing is computing different weighted combinations of these guys at each time. And the weights vary with output time. So the input to the hidden decoder layer at any time is going to be sum over I WIT times HI. So for example, at time 3, this is going to be a weighted combination of all of these hidden representations at the input, where the weights are specific to time 3. These weights are scalars, they're not vectors, right? Now, so what we need is some mechanism to compute these time varying weights. We require a time varying weight that specifies the relationship of the output time to the input time. So for example, if I want a weight that is, say, W2, 3, right? Wait, 1, 2, 3. My time indices might be off. So let's say I want a weight that's W2, 3, right? That means I want a weight that tells me how much this hidden representation relates to this guy over here. And to determine how much this hidden representation relates to this term over here, I need to be able to, now this term has not yet been computed. So what I will do is compute the weight as a function of the hidden representation at the previous time and this hidden representation itself. So the weight that decides how much the ith input hidden representation is relevant to the output at time t is going to be some function of the ith hidden representation itself and the hidden output state at time t minus 1. So the WIT is going to be some function of HI and the state at time t minus 1. Now we also have a second requirement. We want these weights to be a distribution over time for the input. Basically, we want to say what we really want the weights to tell us is how important each of these hidden representations is to the output at any particular time. So you want all of those weights to sum to 1. So the weights might be something like this, where you might find, for example, that the weight for time 3, where the output is supposed to be upfill, is maximum for H3, which corresponds to an input apple. And for the other guys, you want the weights to be small. So this weight function that we compute, it's going to be computed for each time. And we want this function to be of a kind where all of these weights sum to 1. And ideally, the weight is going to be larger at the times corresponding to the inputs that are most relatable to that particular output. So the way we will do it is through a two-step process. First, we will define a raw weight, which at each time, which is going to be some function of the hidden representation and the output state representation at the previous time. So for example, if I want to see what is the weight that I must assign to this hidden representation in computing the output at time 3, my raw weight is going to be a function of Hi and S2, so St minus 1. I will get one such raw weight for each of these hidden representations. I pass the combination through a softmax, and when I put them through a softmax, it's going to convert the sequence of values, the E values, to a probability distribution. And now we will get a proper weight distribution that actually tells you a distribution that gives you the relative importance of each of the input times to any given output time. Now this raw function, the raw weight function, can have many forms. The simplest one, if the hidden representation here has the same dimensionality as the hidden representation here, you could simply have an inner product between the two. Each of them is a vector, so the inner product between two vectors is going to be a scalar. If they are different dimensions, or even if they are the same dimension, you could have a matrix inner product by inserting a matrix between the two, in which case this matrix is a parameter that must be learned. Or another kind of function that has been proposed is one that concatenates both of these two. So remember, if I'm trying to compute the weight for time 1, I'm going to be using S0. So I'd concatenate S0 and the age into one extended vector, zap it down to using a matrix WG into a different vector, compute a tan H, and then compute an inner product with yet another vector V. So in this case, V and W are going to be the parameters of this function that must be learned, that tells me how to relate the hidden state at any input time to the output at any time in the decoder. And those, of course, are going to be compressed into a probability distribution using softmax. So if I were to convert an input to an output, let's say I was given I ate an apple. In the first step, I'm going to pass the input through the encoder to produce hidden representations at each time. Then I need the initial state representation for the decoder, S minus 1. And there are different ways of doing it. If the hidden representations at the output are the same dimension as the hidden representation at the input, then I could just say the S minus 1 is the same as Hn in this case. If they are different, I could say S minus 1 is some linear transformation of this guy, where this term W now becomes a learnable parameter. Subsequently, to produce the first word, I'm just going to use one of my raw weight computation functions to compute a raw weight that assigns, that computes the relative importance of each of these hidden representations to the output at time 0. Then I put this combination, a collection of raw weights through a softmax to get a probability distribution over all of these guys. And then subsequently, I compute a weighted combination of all of these hidden representations using these weights to get this weighted combination vector Z0, which is now going to be input to the decoder at time 0 to produce a probability distribution over words in the target symbol sequence at time 0, from which I will draw a word. Having done this, now I'm going to use the state at time 0 and each of these hidden representations to compute the raw weight vectors for these hidden representations at time 1. And then I compress those into a probability distribution using softmax. And once I've got these weights, which are this probability distribution, I can compute a weighted combination of the hidden representations to get Z1, which is now going to be input to the decoder along with the word drawn at the first time instant. And now the decoder will use these and, of course, the hidden state at time 0 to produce a probability distribution over words at time 1, from which I will draw the second word. And the process continues. Now I'm going to use S1 and each of these hidden representations to compute the raw weights for these hidden representations at time 2, make them all convert them all into a probability distribution using the softmax, use that to compute a weighted combination of these hidden representations at time 2, feed that along with the word output at time 1 to the decoder, which is going to produce my next probability distribution from which I draw a word. So I can repeat the process until I finally output at end of sequence symbol, EOS symbol. Now, of course, again, the objective over here is to find to draw the word sequence which has the highest probability. And simply randomly drawing words is not going to help. Picking the most likely word is also at each time greedily is also not going to necessarily give you the best answer. So what we will actually do is what we did earlier. We're going to, at each time, you'd produce a word, probability distribution over the words. All of the words can be fed as candidates to forked copies of the decoder. And of course, to keep it from blowing up, we would prune it down so that we just keep some top n. And then those are going to be grown again. And then we have as many copies as there are possible words at time 2. We're going to just keep the top k and keep doing that until eventually one of them produces, until the most likely word sequence ends in a end of sequence symbol. Again, as before, the most likely, the first occurrence of an end of sequence symbol may not be the most probable word sequence that ends in an EOS. In fact, that could happen anywhere. So we must continue until we have a word sequence that ends in EOS that is currently the most likely word sequence. Now remember that at each point we are multiplying probabilities. So if this guy is the most likely word sequence at this time, extending any of these guys further is not going to give you a more probable word sequence that ends in EOS. So you might have a situation where this word sequence is shorter, but the most probable word sequence that ended in an end of sequence symbol was actually this guy, right? So you have to keep track of the most probable sequence. You can, of course, also generate the n most probable sequences and so on. Now, there's something very magical about this whole process. This whole mechanism became feasible because we were able to combine all of these hidden representations into a single weighted combination using these weights. And these weights were specific to the output time instant. So we got a different weight, set of weights for each time. Those set of weights are expected to somehow highlight the specific hidden representation that's most relevant to that output. So does this really work? Here's a very nice example from Badanao et al. This is from their, what is the title of the paper? It's in the next slide. But this was for a machine translation task. These are the input sentences. These are the sentences that are output by the network. And this box represents the weights assigned to each of the input times at each output time. So each row over here is going to represent this collection of weights for a particular time. So here this top row is going to shows you the collection of weights when producing the first output word. The second row shows all of the weights when outputting the second word, and so on. And observe something interesting. This word la actually corresponds most closely to the in English. So the weight is greatest at this top left corner. Accord corresponds to agreement. So this weight is greatest. Sur corresponds to on. So this weight is greatest. La corresponds to the. So this weight is greatest. But then when you get to European Economic Area, the word sequence in French is Zone Économique Européenne. The word sequence here is exactly the opposite as in English. And observe how the weights actually caught it. So the zone, for the fourth output word, mind you, these weights have been computed before this word was produced. But for the fourth output word, observe that the largest weight was automatically assigned to the time to area in the input, and so that leads to a correct appropriate decoding of the word zone. For the fifth word, again, these weights are computed before this word is generated. Remember that. So the network automatically assigns the highest weight to economic, which allows it to hypothesize economique. In each case, you can see how the network actually manages to capture the alignment correspondences between the output and the input. Although overall, there's a diagonal tendency because language generally proceeds left to right. Right? So it's a very nice, pretty result. And here are some translation examples from their paper. I won't read it again, mostly because I don't understand French. But I believe that in this case, RNN search is their proposed method. RNN enc is a contrast method which actually is closer in spirit to the first sequence-to-sequence model that I explained earlier, where you compact all of the information into the final hidden representation. And apparently, their method actually results in much better translations, and it actually results in much better BLEU scores as well, as you will see in the paper. So we've seen how a trained network, now that was all about how you can produce outputs using a trained network. So we've seen how a trained network can be used to compute outputs, convert one sequence to the other. But how exactly would you train the network? You're going to be given training inputs, which are source sequence and target sequence pairs. During the forward pass, you're going to pass the actual input sequence through the encoder. So you'd pass I ate an apple through the encoder in this case, but you're going to continue to process through the decoder, and you're actually going to pass the actual output sequence through the decoder. So this is exactly as like what we did when we were training the first sequence-to-sequence model that I explained earlier in this lecture, right? And at each time, the network is going to output a probability distribution over words. You can compute the divergence between the desired output and this probability distribution. So the desired output, of course, is going to be Ishaban and Apfel-Gegessen in this example. And so observe that the desired output is simply this guy shifted left. That's because at each time you're trying to predict the next word given the entire input and the output until that time. So which is why the output sequence also ends up being fed to the network. Once you compute the divergence, you can backpropagate derivatives through the network. And remember that the backpropagation also updates the parameters of the attention function G. So this sort of completes the discussion of the general attention model framework. There are various extensions to it. So Luong et al. Have present variants where instead of producing attention vector, probability attention distribution over the entire input sequence, they have a more localized computation of attention. In the original paper by Bardanau et al., the encoder was not a one directional recurrent network. It was actually a bidirectional LSTM. There are other such variants that have been proposed, and all of them have are basic variants of the different variants of the same basic theme, and the advances to these designs continue. But the basic idea is exactly what I've just presented. We have very impressive results. In fact, attention-based models are currently responsible for the state-of-the-art in many sequence conversion systems, like in machine translation, where the input of speech is text. It should not have been speech, I'm sorry, text in a source language, and the output is text in a target language. Or in speech recognition, where the input is speech audio feature vectors, and the output must be the transcribed word or character sequence for that recording. They're also used for image captioning, and here, but this is a very nice paper called Show, Attend, and Tell from 2016, where instead of working on a word sequence and producing hidden representations for every word in the input sequence, the encoder now actually operates on images using a CNN and produces a hidden representation for every location on the image using the CNN. The decoder works exactly as before, except now it works on this collection of hidden representations, pixel level hidden representations over the input. And as you can see here, for example, this picture was transcribed as a group of people sitting on a boat in the water. And if you look at the weights over all of the pixels, when the word people was predicted, the weights sort of highlight this nice area. Or a woman is throwing a frisbee in a park. It figures out that this portion of the picture must be given the highest weight in order to predict the word frisbee, and so on. So in closing, we've looked at various forms of sequence-to-sequence models, which are generalizations of the recurrent neural network formalism. For more details, please refer to some of the papers that I've listed on the slides, but you can get a lot more information on the web. And if you have questions, please post on Piazza. Now, sequence-to-sequence models are going to appear in your homework 4, where you're going to use sequence-to-sequence to recognize speech. So you're going to actually be working with these models. Thank you.